Hello and welcome. Thank you for spending time with us today for part 4 of our Instant Insight series on biomaterials and medical devices. My name is Troy Nickel and I'll be your host today. I'm a product manager here at TA Instruments. It's my pleasure to introduce our speaker, Greg Kamikowski. Greg is a senior application scientist for rheology and works out of our office and lab in Chicago. If you've met Greg before, you probably know this already, but he's a huge Cubs fan. He also has a BS in chemistry from Loyola University in Chicago and a PhD from University of Wisconsin-Madison. In his industrial positions, he's always focused on rheology. He's a member of Society of Plastic Engineers, Society of Rheology, and ASTM. Greg also loves to answer questions. So, after Greg presents, I'll relay questions that you submit during the seminar. You can do this in the Q&A tool in the lower left of your screen. So with that, Greg, thanks for presenting today, and I'll now hand it over to you.
Thank you for the introduction, and I appreciate that, Troy, and welcome everybody to this seminar on the rheology of soft biomaterials. This is actually the 9th out of 12 seminars that we application scientists from TA Instruments and Waters are presenting in this month. And hopefully you've had a chance to see some of these live, but if not, they will be archived, and you can view them when it's convenient for you to do so. Here are the topics we will cover in this presentation. We will go over the fundamentals of rheology for those people that are getting familiar with this topic. We'll look at the TA Instruments rheometers and the geometries that we would use with them for our testing. We'll go over testing methodologies as well. And we will use these principles to discuss the rheology of things like hydrogels and creams, adhesives, drug capsules, and biopolymers. And so this is where we usually begin, and that's what's rheology? It's the study of the flow and deformation of matter. And as we show in this diagram here, it's practical for every aspect of our lives. Car tires, medical devices, pharmaceuticals, food, lotions, polymers, asphalt, and we're going to focus on the biochemical parts in this seminar. So when we say that rheology is the study of the flow and deformation of matter, we mean that when we look at flow properties, we're looking at how liquids behave, we're looking at the viscous properties of material. And we illustrate that with this dashpot in which we pull a piston through a cylinder that has a fluid in it. And what we know is that the force depends on the velocity of the material, the velocity at which we are pulling the piston, and it's independent of the displacement. On the other hand, when we look at deformation properties, we're looking at how solids behave, we're looking at the elastic nature of a material. And we illustrate that with a spring in which the force depends on the displacement and it's independent of the velocity. So it's just the opposite of what we have with fluids. But the materials that our customers will be evaluating are a combination of both viscous and elastic properties. So we call them viscoelastic. So how does a rheometer work? The rheometer measures the viscosity and viscoelasticity of fluids and semi-solids and solids by imposing deformation and measuring the torque or vice versa. So this is how a rotational rheometer works. And the things that we measure are the viscosity of a fluid, which is the resistance to flow, and that's a function of time, shear rate, shear stress, and temperature. And as we said, we can also measure the viscoelasticity, which is a property of materials that exhibits both the viscous and elastic behavior. So we will concern ourselves with measuring parameters like G prime, G double prime, and tan delta that we will describe a little bit later. The reasons that we do rheological measurements are shown here. One is we want to do characterization of the materials, and that would be like for a synthetic chemist who's made some materials in a lab, and you want to see what the effects are of changing formulation or catalyst or synthesis condition. We want to find a way that enables us to measure the molecular weight and molecular weight distribution of the material, and also measure things like the state of flocculation or branching and properties like that. We also do rheological testing to get an idea of the processability that we would expect of our material when we're trying to use it in real-life applications like extrusion, blow molding, and pumping, and operations like that. And finally, we use rheological testing to enable us to determine the end-use properties of our material. How strong is it, and what are the temperature, what's the temperature range over which we can use the material and not have it fail? What will happen when we do the rheological testing is we will convert machine parameters to the fundamental rheological parameters. So for a rotational rheometer, we'll convert angular velocity to the shear rate, the angular displacement to the shear strain, and torque to the shear stress. When we're working with materials that are more solid-like, sometimes it is more convenient to measure their rheological properties in a linear mode. And we have some devices that can test solids like this in a linear mode, these dynamic mechanical analyzers. And with these instruments, we convert the linear velocity to the extension rate, the linear displacement to the tensile or flexural strain, and we convert the force to the stress. So here are the parameters that we use when we do rheological testing. The shear rate is usually denoted by the Greek letter gamma with a dot over it. The elongational rate is epsilon with a dot over it as well, and the units on that are reciprocal seconds. The stress parameter in shear is usually denoted by sigma, and in elongation by tau, and the units are pascals, which are newtons per square meter. Sometimes I've seen this just the opposite, where people have used tau for shear and sigma for elongation, but most of the time sigma is used for shear and tau for elongation, and generally it'll be obvious from the article that you're reading what they are referring to. And then viscosity is the stress divided by the shear rate, and we have this in both shear and in elongational forms. For solid-like materials, the shear strain is denoted by the letter gamma without a dot over it. Elongation is epsilon. The stress, again, is sigma and tau. And if we impose an instantaneous strain on the material and measure the stress, we get the modulus of the material. This is the stress relaxation test that is mentioned here. And if we turn that around and impose a stress and measure strain, we get the compliance of the material. So this slide shows a number of materials that we encounter in everyday life, and it shows you the range of viscosities of some common products. The preferred units for viscosity are Pascal seconds, but some people prefer using poise, and in some cases when we're working with low viscosity materials, it's more convenient to use units like centipoise or millipascal seconds. So for example, water at 20 degrees C has a viscosity of 1 centipoise or 1 millipascal second. These are the rheometers that we sell. We have the HR 10, 20, and 30, and these were just introduced in early March of 2020, and these are replacing the very successful DHR rheometers that we had for several years. The way that we would describe the HR rheometers is the native mode is controlled stress, single head, and combined motor and transducer. The Aries C2, which you see on the right, we've had for quite a while. This replaced the Aries rheometer several years ago, and we describe this as controlled strain, dual head, and separate motor and transducer. For the HR rheometers and the Aries, we have the schematic diagram of both of these here. And if we look at the HR type of rheometer on the left, you see that the way this works is we apply a torque through a non-contact drag cut motor, and we measure the amount and rate of deformation with 1 or 2 optical encoders. And that's essentially how the rheometer works. So everything happens upstairs, so we call this a single head or combined motor and transducer. On the other hand, if you look on the right, we show the schematic of an Aries G2 rheometer, and that has a unique design to it. The motion actually occurs on the bottom with a direct drive motor, and the torque is measured through a force rebalance transducer. So it measures the torque that's transmitted through the specimen. And the benefit of the Aries design is that this is essentially an inertia-free measurement. And this becomes an issue when we do oscillation on weak structures, and especially as we go to higher frequencies. So there are materials where we can get measurements with an Aries that are difficult to get on an HR or not even possible. So one of the things to point out is with the computer feedback that we have between the instrument and the computer, the HR rheometers can do controlled rate and controlled strain experiments, and the Aries G2 can also do controlled stress instruments, even though those are not their native modes. This shows the different geometries that are used for rheological testing. We have concentric cylinders, cone and plate, parallel plate, and for materials that are fairly solid, we can do torsion rectangular testing. The geometries that we're showing here are those that were used with the that are used with the HR rheometers, and the geometries for the Aries are similar, but they are designed specifically for the Aries G2 rheometer. And this slide shows what the different geometries are typically used for. So concentric cylinder is used for coatings, beverages, from low viscosity materials. It's also used for slurries, so we can use a vane rotor and get viscosities on some slurry systems. We have a starch pasting rotor that goes with the concentric cylinder. Then there's a cone and plate geometry, which is good for low viscosity fluids. And it's also good if we have just a sparse amount of material, as this does not require much volume for testing. But the next geometry, the parallel plate, is the real workhorse of the industry. And this is used on just about any kind of material that you would work with. So it's used successfully on adhesives, melts, hydrogels, asphalt. It's used in curing studies, foods, cosmetics. So it is used in just so many applications. And then we have the torsion rectangular fixture, which is used for things that are primarily solid. As I had mentioned, there are times when it's more convenient to test solid-like materials in a linear mode. And we have some instruments that are designed to do that exclusively. So these are our dynamic mechanical analyzers, and that's the DMA 850, the RSAG2. We also have dynamic linear capabilities on the Aries G2 and the HR rheometers. And we have a line of instruments from our ESG group, and the 3200 is capable of doing dynamic mechanical analysis as well. So the DMA 850 is analogous to the HR. It's a controlled stress instrument in its native mode. It's a combined motor and transducer. And the controlled, the RSAG2 is like the Aries G2. It's controlled strain, separate motor, and transducer. And so this is the schematic, and it shows the workings of an 850. Again, everything happens down here. We have the motor that applies a force, and we have the optical encoder that measures the amount and rate of deformation. The RSAG2 is like the Aries G2. In this case, the motor moves the lower geometry up and down, and we measure the force with the force rebalance transducer. And again, this is essentially an inertia-free measurement. This shows the clamps that are used on the DMA, and these are the clamps specifically for the DMA 850. And the two most common clamps that are used with the 850 are the single and dual cantilever and the film clamp. With the RSAG2, we have similar clamps, although they are machined specifically for the RSAG2. And in that case, the most popular clamps are the film clamp and the three-point bend. Well, let's look at the different methods that are used to characterize things in a rheological way. So let's start with unidirectional testing. So we'll begin with flow testing, where we could do a stress or a rate ramp, and do a stress or rate sweep. We can do a test where we get viscosity versus time. On the HR rheometers, we call that peak hole on the Aries G2, that's stress growth. And we can get viscosity versus temperature. And then the other unidirectional tests that we can do with these instruments are creep, stress relaxation, and we can actually do unidirectional axial testing on these rheometers as well. Now, the graph here shows the difference between a ramp and a sweep. So if we plot the, let's say, the shear rate versus time, with a ramp, it's always increasing in either a linear fashion or an exponential fashion. And we can do that as a stress ramp as well. But the thing about that is our geometry is always accelerating, so we never get to equilibrium. And sometimes that's not an issue, like for some viscosity standards. But in some cases, it is definitely preferable to use the sweep, which is what we're showing here. And with a rate sweep, we'll go to a certain rate, let the system equilibrate, make our measurement, and then we go to the next rate. And we can do that as a stress sweep as well. So we enable the system to equilibrate, and that takes away some of the effects that inertia might have on our measurement. And so the first results that I'll show from flow testing is this happened to be a stress ramp. It's a stress ramp up, stress ramp down. And the purpose of this test is to look at how much damage is being done to the system as a result of flowing. So we have these structured fluids, and they lose their structure when flow is imposed upon them. So the way we one way we can measure the amount of damage that's done is to do either stress ramp up, stress ramp down, or we could do a rate ramp up, rate ramp down test. And what we do is we look at the area in between the two curves, the up curve and the down curve. So you can see that the mayonnaise curve has not much change with the two curves, so there's not much damage being done. And the word that we use that describes the amount of damage that's done is called the thixotropy of the material. So you can see that the mustard has more damage being done as this down curve is of a lower stress than the up curve. And the ketchup shows quite a sizable amount of damage. There's a lot of thixotropy with this system, as evidenced by the big difference between the up curve and the down curve. Looking at ketchup once again, we can also do this just as a stress ramp up test to get the yield stress of the material. So in this case, we apply a stress until we get some definite flow in our system. And the way the yield stress was determined here was the operator just drew a straight line once the material started flowing and extrapolated to the y-axis and estimated a yield stress of 56 pascals. Another thing you could do is you could fit the data to a model, or you can also just look at a graph like this and look at where you get the knee in the curve, and you can call that the yield stress. But whatever you do, just as long as people are knowledge or familiar with the method that was actually used to determine the yield stress. In the graph that I'm showing here, we show viscosity versus shear rate, and this is the typical way of showing flow data. We have viscosity versus shear rate, and these data points were obtained with a rate sweep. So we got equilibration at each rate, and then took our measurement, and then we proceeded to the next rate. And we have a very wide range of different flow behaviors here. We have some low viscosity Newtonian material. We have high viscosity Newtonian material with the syrup. If we look at the copolymer, it shows a very common shear thinning behavior that we expect from polymers. And we have some other materials that show some very strong dependence of viscosity on shear rate. So if we look at the cocoa butter lotion, what we see is that it is very shear thinning to the point where it looks like what we would call power law behavior over most of the experimental shear rate region. And one of the things interesting here is the starch mixture. It starts out Newtonian, then it shows some shear thinning, and then it shows some shear thickening behavior, which is an interesting property of starch and some other material as well. But generally, we see shear thinning behavior with polymeric materials. We can also do these sweeps as stress sweeps, as we're showing here. And in this case, you can see that there is a drastic difference in properties when we go from 0.34% to 0.43%, to the point where it indicates that at 0.43%, we now have some definite structure being formed, and we get to the point where it looks as if we are getting some mild yielding behavior of our material. And then as we go to higher concentrations, we see that the viscosity is much, much higher in the very low stress area. And then as we proceed, we get more and more drastic yielding behavior for our materials. On this graph, we show viscosity versus temperature for a printing ink. As you would guess, the viscosity decreases as a function of temperature. And it's important to know how the material will change as a function of temperature. So we've talked about several of the unidirectional tests, especially the flow test. But a big reason why people will get a rheometer is to get the viscoelasticity of their material. And the most common way of getting viscoelasticity is to do dynamic oscillatory testing, as we've illustrated here. So in the diagram in the upper right, you see how the upper geometry is going to oscillate in a certain way. And we can impose a sinusoidal strain or a sinusoidal stress on our sample and get the response. So let's just say that we are imposing a sinusoidal strain with an amplitude of gamma 0 and an angular frequency of omega. A lot of the times we will think about frequency in terms of cycles per second, but in this case we're looking at it in radians per second, and the conversion factor is 2 pi, or 6.28. So 1 hertz, 1 cycle per second, is 6.28 radians per second. So if we have a purely elastic material like the spring on the right, we would see that the stress response is in this perfect alignment with the strain wave, and that's because the stress response for an elastic material is purely dependent on the displacement. So these two waves are completely in phase. If we had a completely viscous material, we see that the wave for the viscous material is shifted 90 degrees or pi over 2 radians. And the reason for that is because this is totally a rate-dependent phenomenon. But the materials that most people will be looking at are somewhere in between being completely viscous and completely elastic. So here are the parameters we will be working with in dynamic testing. There's the strain that we are imposing on our sample, and there is the stress response. And the parameters that we use when we analyze our data are G prime, which is the storage modulus, which is a measure of the elasticity of the material. G double prime is the loss modulus, it's a measure of the viscous nature of the material. And if we take the ratio of G double prime to G prime, we get tan delta. If we take the ratio of the stress magnitude to the strain amplitude, we get the complex modulus of the material. And if we divide the complex modulus by the angular frequency, we get the complex viscosity. And this is an extremely useful parameter in the world of polymer melt rheology. It's also useful with some other systems as well. And that's because it says that the complex viscosity at a certain angular frequency is equal to the steady shear viscosity, where the angular frequency is equal to the shear rate. So what are the different kinds of dynamic tests that we can do? We can do a dynamic stress or strain sweep, a dynamic time sweep, frequency sweep, temperature ramp, temperature sweep at one or several frequencies if we want. And if you have a stable material, the first test that you might do would be a dynamic strain sweep. And what we are after is trying to find what we call the linear viscoelastic region for the material. And this is where the storage and the loss modulus are constant as a function of the strain. So, in the region here, a little bit below around 1% and below, we see that the storage and loss modulus are flat, and we call this the linear region because the stress and strain are perfectly linearly related here. As we go to higher strains, you can see that we are doing some damage to our system, and we see a change in storage and loss modulus. And this change that we see is typically more prominent with the storage modulus. It's usually the more sensitive parameter when it comes to looking at the structure of a material. We can also do a dynamic stress sweep, and in the situation that we're showing here, we are doing a dynamic stress sweep on mayonnaise. And we can look at the value of the storage modulus in the linear region to get an idea of the strength of the material. And we also take note of where the material yields. And there are a couple of ways of determining this. In the example that is shown here, the operator drew these two tangent lines and recorded the point where they intersected and called that the yield point. Sometimes people will just use the last point at which you see linear viscoelastic behavior. So if I look at this graph, I would see that you might say the yield point is more like 20 pascals as opposed to 53.8. But if you report a dynamic yield stress, it's important that you describe how you obtained that yield stress. Frequency sweeps are very useful tests on a number of materials. Here we're showing frequency sweeps on cheddar cheese at two different temperatures. At the low temperature, where the material is more solid, we get the following frequency sweep where we don't see much change in the storage or the loss modulus as a function of frequency. Yeah, we are seeing a change, but it's certainly not as dramatic as what we see when we go up to 50 degrees C. So it's kind of a regular descent as opposed to looking at how the material behaves at 50. We see that the storage and loss modulus dropped very significantly, and eventually we would expect the storage modulus to drop to zero. But this is the typical behavior that we see with cheese at a temperature like 50 degrees C, and this is also the kind of behavior that we see with uncross-linked polymer melts. We see that at the low frequencies, they have lower elasticity than they do viscous nature, but as we go to higher and higher frequencies, we see that the elasticity begins to dominate over the viscous nature. And in this situation here, we do see this crossover point, and many times it is useful to note what that is. Either, we'll note both the frequency and the modulus and use that as some kind of a reference point for characterizing our materials. Here is a dynamic time sweep on a silicon-based hydrogel in which the material is gelling as a function of time. So we get the storage modulus being lower than the loss modulus at the beginning, but as the reaction progresses, you see that the storage modulus is gaining on the loss modulus. We get a crossover point, and then the material continues its curing, and G prime, the storage modulus, continues to increase. It's good when we have a crossover point like this. It is a convenient milestone in the course of the experiment. Sometimes we don't see that, and we have to come up with some other ways to note certain milestones in the test to describe when the material has gelled. We might look at when the complex viscosity or when storage modulus reaches a certain value, and we may use that instead. Here is an example of a temperature ramp. So this would be done at maybe 2 or 3 degrees C per minute. And in this case, the way the experiment was done was it was begun at 70 degrees C, and then the temperature was lowered down to 10. So at 70 degrees C, it is more viscous than it is elastic. And then as we go to the lower temperatures, you can see where it begins to be more elastic than it is viscous. So in this region here, closer to 10 and up to about 50, the material is the cheese is more elastic than it is viscous. And this is an important characterization of the material. Okay, let's use that basics that we just went over on rheology and apply that to biopolymers. So one group of materials that we'll talk about are hydrogels and creams, which are soft matters that contain a high level of liquids such as water or oil, and they're used in a number of applications like tissue engineering, wound patching, drug delivery, contact lens, and these super absorbent materials. And rheological testing is important in terms of characterizing the materials and being able to predict how they will perform in real life applications. So we begin with a frequency sweep on the natural polymer hyaluronic acid, and this looks similar to the frequency sweep that we showed on the molten cheese. And the properties that we note here are that, again, at the low frequencies, the storage modulus is low and it's trending downward. The loss modulus is higher in the low frequency region. It's also trending downward, but not as much as the storage modulus. And then as we go to higher frequencies, we get this crossover point, and beyond that, the material is more elastic than it is viscous. And on this graph, we also have the plot of the complex viscosity, and we can use that Tex-Mertz transformation to predict what viscosity versus shear rate would be, and we can fit that data to a flow model, which will help us to predict the processability of a material like this. Now, in this case, we're going to be looking at the gelation of this hyaluronic acid material, and as we saw before, we're going to do a dynamic time sweep, and conveniently, we have a crossover point with this system as well. And at the end of this test, we can do a frequency sweep. And what this will tell us is how strong our gel is. And the fact that the storage modulus here does not change much at all as a function of frequency indicates this material is really elastic, which is what you would expect. So again, we have very little change in the storage modulus as a function of frequency on this nearly completely gelled material. We can do temperature ramps on gelatin materials, and we can start the test like this at 50 degrees C, and as we go down, we reach a point where the material starts to gel. That's what we're picking up around 25 degrees C. And then we go down to 10, and it is still in the gel state, but we could bring it back into the liquid state by just heating it up, and you can see that we generally have to go to higher temperatures to liquefy the material again to break down the gel than we did when we did the cooling. But in this case, you can see we get pretty good results with 1 degree C per minute or 2 degrees C, and this is a way for us to characterize a gelatin gel. We can also look at the properties in the low temperature region, which is what we're doing here, and we look at how the modulus changes as a function of the gelatin concentration. And we can see that at a concentration of 1%, we really can't even call it a gel, just because the the storage modulus is decreasing without end. So no real apparent gel in that case. But if we go to 2, 3, 5, and 10%, we see that the strength of the material increasing, but we also note that we get that same curve that we just saw, where the storage modulus does not change as a function of the frequency. So this is a very solid material, and the strength of the material will vary based on the concentration of the gelatin. Here's a test that was done on contact lens. And it was just a simple frequency sweep where we compare the contact lens from two different vendors, and you can see these are substantially different. Definitely a different frequency dependence on tan delta. You would expect there would be some difference in the field for these materials if one had a contact lens from A and one from B. And in this case, what we're doing is we can do this test on an HR rheometer, where we submerge the sample with this submersion accessory. We also have a fixture for the RSAG2 that was designed specifically for contact lens, and that will enable you to get the viscoelastic properties of the contact lens material. Here's some stress relaxation testing that was done on an eye patch. So, when you put this on your face, it's important to know how much strength the material has and how that strength is going to change as a function of time. So in this case, the stress relaxation is a useful and practical test for us. Let's talk a little bit about lotions now. One of the things that we're concerned about is the stability of these materials. And one way we can get that information is to perform a dynamic strain sweep. And we see that these two emulsions, A and B, are similar in this low strain region, but sample B degrades, it goes into the nonlinear region fairly early, whereas material A retains its strength up to fairly high strains. So our prediction would be that emulsion A has the greater stability than does emulsion B. Some other testing that we could do on lotions, we can do dynamic frequency sweeps, and what we would look for is to see how tan delta behaves as a function of frequency. And we like this to be flat, not change too much, and we view that as an indication of good stability for this material. Another interesting test that you can do with the lotion is to impose shear on it so that you break down your structure and then stop the flow test and then do a gentle oscillation on the material to see how the structure is building as a function of time. And generally, we like that to occur quickly once the flow stops. Here we have a temperature ramp on some lotions, and let's just look at A and B. These come from the same supplier, but material B is formulated to give you UV protection. And the one thing that you note here is that the material B that has the UV protection formulation has greater thermal stability compared with just a regular hydrating lotion. You see the big drop off in G prime with the hydrating lotion at a much lower temperature than what we see with the UV protection material. Another way that we can use rheology on lotions is to do several temperature ramps. So we cycle the material up and down in temperatures and use that information to predict the stability of our material. One of the things that has become more popular in characterizing lotions as well as food, is tribology, which is the study of the wear and lubrication of materials. And the idea is that the tribology testing will correlate with sensory appeal. So here are the different geometries we have for tribology. It's ring on plate, 3 balls on a plate, ball on 3 plates, 4 balls, and you can use whichever is the most convenient for us to work with. So in this case, we're looking at the coefficient of friction, which is the main parameter that we get from tribology testing. And these are 4 commercial lotions. And what's interesting is that each one has a unique behavior to them in the application window. So the idea would be that with tribology testing like this, people would be able to recognize differences in the feel of these lotions when they're applying it to their hands. There's also been interest in doing tribology on food to relate that to the sensory perception in the mouth. So in this case, we tested 3 different chocolates, and again, you can see that each has a unique behavior in terms of its coefficient of friction as a function of the sliding speed. Now let's look into some biomedical adhesives. These can be used to attach to hard or soft tissue, and as you would expect, rheology is very important in terms of processing these adhesives and then having them perform in their real-life application. So one of the things that we're interested in is viscosity versus shear rate, and we see that the low shear rate region should correspond to the stability of our material. The higher the viscosity is, the more stable the material is. When we go into the mid-range between 1 and 10 reciprocal seconds, that correlates to things like transporting, mixing, stirring, and pipe flow. And then most of the time when we apply these adhesives, that's done at a very high shear rate. So we're going to look in the region of shear rate of perhaps 100 to 1,000 reciprocal seconds. One of the tests that's extremely useful for adhesives is tap testing, and that can be done as a unidirectional axial test on our rheometers. And probably the most common geometry that's used is the 8 millimeter parallel plate. So we can look at the force versus the displacement and record the maximum force that we achieve when we separate the top plate from the adhesive. And we can also look at the area under the curve to get an indication of the work involved with breaking these bonds. Another test that we can do with the rheometers is a peel test, a T-peel test. And we have just developed a newer version of the extensional rheometer, and we call that the extensional viscosity accessory. And that has an accessory to do T-peel testing like this. Generally, it's used to get extensional viscosity of polymer melts, but it can be used to do T-peel testing like what we're showing here. Probably the most important test that is done on an adhesive is a dynamic frequency sweep. And we can correlate the different frequency regions to the different applications for an adhesive. So if we look in the low frequency region, we can correlate that to the creep of the adhesive under a load. If we go to about 0.1 radians per second, we can get an idea of the tackiness of the material. And if we go to very high frequencies, we can predict the peel strength of our material. And of course, it's useful to do dynamic temperature ramps on our adhesives to look at how the mechanical properties change as a function of temperature. So one of the things that we typically see with polymers is a peak in tan delta that indicates a glass transition temperature. And we also have some other points of interest that we might note in characterizing a material. So we can have this Dahlquist temperature that I believe is where G prime is 300 kilopascals. We have this plateau modulus for our material, and then we have this crossover point where the storage modulus finally goes below the loss modulus, and now it's essentially a thermoplastic melt. So those are things that enable us to quantify or we can specify certain properties of our adhesive material. An interesting application of adhesives are adhesives that are UV curable. So an example of that is dental adhesives. And what's interesting here is how quickly in this case, the complex modulus rises about 5 decades of strength in a matter of a few seconds. And it's impressive that the rheometers can catch this growth. And you can see the points all along the way as the material strengthens and then eventually gets into its fully cured state. Another issue with adhesives that are cured is that they will show some shrinkage upon curing. And that's an important property to be aware of. And we can measure this shrinkage in 2 ways. One is we can keep our gap the same when we do this curing and measure the force buildup, or else we could control the force at, say, 0 newtons and measure the change in the height of our gap. And this will give us an idea of how much shrinkage the material will undergo as it's being cured. Now let's talk a little bit about drug capsules. These are made from gelatin or polysaccharides like HPMC. And again, rheology and DMA are very important ways of characterizing these materials that we're using in drug capsules. So in the example that we're showing here, we illustrate the moisture sensitivity of a gelatin capsule, and we do this by using our RH accessory on either the DMA 850 or one of the HR rheometers. So this test is done isothermally, but as time progresses, we're doing a humidity ramp. And you can see how going to the higher humidity plasticizes the material, and we get a drop-off in the mechanical strength of the material. So that's important to note when it comes to gelatin capsules and a number of other things as well. So in this case, we're making capsules out of HPMC, and what's interesting in this graph is that we're doing a temperature ramp, and it begins as you would expect, where the material gets weaker as temperature goes up. But then at some point, the gelation kicks in, and now the storage modulus rises pretty dramatically. We get the crossover point again, and the material becomes fully cured. And the way that we use this information is that when people make these capsules, they'll stick a hot pin inside a cold solution, and you'll get the material gel against the pins. So, talking about biomedical devices now, this has so many applications, and there are so many different polymers used in this application. And in each case, the rheological properties of these materials is very important in terms of their processability and to how they're going to perform in our real-life applications. So one example that we have here is the polylactic acid, which is biodegradable, good processability, and it's low cost. And it's been used in a number of applications like those shown here: orthopedics, drug carriers, stents, tissue engineering, antimicrobial agents. And we can use rheology to tailor the molecular characteristics of the polylactic acid, and that will enable us to predict the processability as well as the final properties of our material. So we can do a temperature ramp to see when the material liquefies and can be processed like a polymer melt. And then we can cool it down to see when it solidifies and what is the final strength of the material when it does solidify again. So we show the storage and the loss modulus here, and we show the complex viscosity on the graph on the right. So you see what happens when we heat, and then after that we start cooling the material. And then after we've made our part, we might want to do a dynamic temperature ramp to determine the mechanical properties and the transition temperature of our material. So you can see that the storage modulus begins a sharp descent at about 60 degrees C, and we get these associated peaks in the loss modulus and tan delta. And generally, the tan delta peak is identified as a glass transition temperature. Then you can see when the material gets to be in molten form as well. Let's talk about some special applications with some different geometries. So one of the tools that we have to measure starch is the starch pasting cell. And to characterize starches, there is an established method where you start mixing the material at allowed room temperature, then you do a fairly rapid temperature ramp, you hold it, then you go down in temperature, and then you hold it there. All the while you are rotating at about 160 RPMs. And note that the rotor has a unique design for starch pasting. And we've seen that this has good applications for just about anything. If you want to use this as a mixture of powders and things like water, that the starch pasting rotor has a very nice design to it for mixing. So here we've shown the starch pasting graph for the hydroxylated dent corn, and we'll note things like what's the pasting temperature, which is where the viscosity begins to go up, which is going to be at about 200 seconds here. We note the peak viscosity. We note the holding strength, which would be the viscosity when we're at the high temperatures. And then after we cool the material down, we'll record the final viscosity of our starch mixture. And what's nice about doing this on a rheometer is after the whole test is done, you can also get the viscoelastic properties and not just the viscosity of the material. Another interesting accessory that we have is the interfacial rheology accessories. So some years ago we came out with the Denoy ring, which is placed on the surface of a liquid, and then we oscillate to determine the interfacial rheology properties. In more recent years, we went to the design that's shown in the upper left here, where we have what we call the double-walled ring, and we use an annular type of geometry there to load our specimen. So again, this is going to go on the surface of a fluid, and most of the time what we'll do is we'll have a fluid in contact with air, and that's where we're doing our measurements. We can also do liquid-liquid interfacial rheology if we want. So that can be done as well. But in the example that we've shown here, we have a protein solution, and the protein is forming a gel in the top layer of the mixture. And we can measure the storage and loss modulus of the material in that state. But what we note is if we put a surfactant on this mixture, we can break up the structure to some degree, and you can see the corresponding decrease in the modulus of the material. Another interesting test that can be done is what we call the Laus test. So this is done on slug petal mucus, and it is simply a dynamic strain sweep in which we go into the nonlinear viscoelastic region. And when some people do this, all they do is they'll just look at the apparent values of G prime and G double prime in the nonlinear region. But if you go back to this publication from 2008, there is a more elegant way of characterizing the properties in the nonlinear region. So we come up with parameters like the stiffening ratio, the thickening ratio, that give the characteristic of your material in the nonlinear region. And sometimes that can give you some important information in terms of fingerprinting your material. And then finally, we have the accessory with the modular microscope accessory, which we're showing here. And this gives us a chance to compare the visual properties that we can see with the rheological properties that we are measuring simultaneously. So here we look at native collagen gels at different concentrations, and we look at their gelation process, and we can look at the corresponding images from the modular microscope to get an idea of what's going on with our system and why we're getting the gelation, why we're seeing the properties that we are getting. So in summary, rheology is a powerful tool for investigating the viscosity and viscoelasticity of biopolymer materials and biomedical devices and just about every other material that we come in contact with. The materials could be liquids, semi-solids, gels, solids, anything. There is a way that we can do rheological testing on these materials. And the reasons that we do this are for basic research and characterization. Rheological testing can help us do troubleshooting with materials when they arise out in the field. And we can use rheology as a QC tool just to make sure that we're making things on a consistent basis. And when you achieve that, you will truly find that rheology is a lot of fun. You make predictions or you solve problems with rheological testing, and it's a very gratifying thing. So we presented a lot of information here, and if you want more information, there is a lot on www.tainstruments.com. And we can look at a number of videos that we have up there, including these specific seminars, the seminar series, Instant Insights, and we have some others there that are useful. If you go to support, there are a number of things there. One of them is the application notes library. And Finally, you can look at products and accessories for all the different instruments that we have, and that should provide you with the information you need on what accessories might be particularly useful for you. Okay, so with that, I thank you for your attention, and I hope that the information that was presented here was useful for you, and you have a chance to do some fun rheology in the near future. Thank you.
Thanks, Greg. That was excellent. Thank you for covering so much great ground, and certainly in the end to remind us that rheology is fun. I have a few questions for you. Man, we have a number of good questions, so I will not get to all of them, but I'll grab a few of them, relay them to you, and then the rest of them you can send via email to the specific person who asked. So I have a couple questions here on molecular weight distribution. I'll ask them both here, and then I think you can answer them together. How molecular weight distribution is determined using a rheometer? That's one question. And you mentioned that you can obtain molecular weight distribution using a rheometer. Can we determine a bimodal distribution if two potential molecular weights are present in the solution?
Sure. And the way that we obtain molecular weight distribution from doing rheological testing is we have to do frequency sweeps. And one thing that's important is ideally we would get to the terminal region where the G prime is heading toward 0. It has a slope of 2. And you would also see that we are in the Newtonian region, in the low frequency region. And then it's good in the high frequency region to get to the point where G prime is almost constant. So we're getting into the glassy regime. And what this will do is it will establish a number of relaxation times. There's an algorithm in our TRIO software that will convert all these, the G prime and G double prime data to a molecular weight distribution. And what would probably be the most useful is I could get some articles that kind of show how this is done. It goes through some of the actual math, and with that, the questioner can find out exactly how it's done on a mathematical basis. Now, the thing is, when you do the determination of molecular weight distribution, it will ask you ahead of time, is it a monomodal, a unimodal type of distribution, or is it bimodal or multimodal? And it helps if you know that going in. It's still a little difficult to go from a rheology program and getting molecular weight distribution to what you would get on a GPC. So they actually work pretty well together when you get data from both. But if someone has a material and they say, well, is this unimodal or is it bimodal? I don't know. Will the software tell them? Not necessarily so. It's still a little bit difficult to do that.
Okay, thanks, Greg. Here's another question. Which geometry do you suggest for foam samples?
For foams, I guess I would probably go with parallel plate compression, and in some cases what you would do would be to glue a foam to the parallel plates if you're concerned about contact or having a nice uniform contact. But yeah, I would probably do a compression test to get the properties of foam materials. That would work probably the best.
Okay. So that's one of those materials.
Foam.
One of those materials that's kind of in between the viscoelastic, the viscous part, and the truly solid. It sort of lands between. So I think what you're saying is you could use a rheometer to do some linear tests, or you could even shift over in the DMA space.
Yeah, absolutely. And the thing is, foams could be varied. They could be soft foams, they could be rigid foams. And, I guess in general, I would think that compression can probably do a good measurement for most foams, but if they're getting very strong, you might consider something like either cantilever or three-point bend. If they're very soft, you may even convert that to tensile testing. So yeah, and everything I've mentioned right now is linear testing.
Okay. Another question on samples, this one in the liquid form. So this, just for context, this question came in when just after you covered the tribology section. It says, how much sample is needed to run these experiments?
The tribology experiments?
I think that's the context, yes.
Okay, that'll depend on which of those different geometries you are using. In general, I would say it's probably just a few mils. I think with every test that we mentioned, I don't think any one of them uses more than probably more than 5 mils. So it's not all that much consumption of material to do tribology testing, or for that matter, just about any kind of rheology test. Especially like parallel plate and cone plate. Sometimes concentric cylinder might take over 20 mils, but that's on the high side. So,
okay.
For tribology, probably just a few mils will be more than enough.
Okay, I'm going to do one last question, and then we'll do the rest via email. You talked about this a little bit, but maybe just to revisit real quick, how to correlate on gelatin tests the rheometer results as a function of time. How do you correlate those to the practical gel point in a cross-linked material?
Well, generally, what we see is that when you go beyond the gel point and the G prime is now higher than the G double prime, right around that point and a little bit afterwards, what you'll see, what you'll see is the material pretty much has a permanent shape to it. And then the question would be is how does a person define the gel point in their own operation? And I think what some people will do is they'll take the material and they just tap on it occasionally to see if a stick or something remains behind, or does it pull material, or does it just tap it, so now it's gelled. And what I would say is that when they do rheological testing like this, they should get an excellent correlation between a crossover point like this, if they get one, and what they might be calling a gel point in a practical sense. So they might be doing it phenomenologically by just doing a tapping test and see what kind of response they get. But I would say our measurement is more accurate and precise, but it would correlate well with the practical test that someone might be doing right now.
Okay. Perfect. Thank you, Greg. I think we'll wrap up here. You've done a great job, covered a lot of ground. We certainly appreciate your presentation and your time. Thank you for all those who asked questions. We will be getting back to you if we didn't answer it live here. So with that, I thank you everybody for your attention. Thank you, Greg, again. And if you want to rewatch this at some point or catch some of the other seminars that Greg laid out in the Instant Insight series, those archives are available on our website. Thank you, everybody. Have a good day.
Thank you.